first part of this chapter deals with radical functions. So a radical function, as opposed to a radical equation that we've solved and stuff like that, that's when you can have any function inside of your square root. So far, we've graphed things like the square root of x. What we're going to be able to do by the end of today is be able to graph the square root of anything inside. So what does the square root of log of x look like? How would you do that? Okay. What does the square root of 5x minus 2 all cubed minus 7 look like? So we can put any function that we are able to graph up till now. We now add a special idea or set of rules, and we'll be able to graph any function we do know up till now inside of a square root and see what that looks like. So there's your basic parent graph of a square root graph, and you could already do all the transformations with that one. What we're going to look at is, well, what's another way? How could we use the graph that we know on the inside to help us graph new functions? So here's one you already know. The square root of x plus 4, you could use transformations and move your square root graph 4 to the left. Perfect, right? Now, if we look at the original function on the inside, so I'm going to underline the x plus 4 in red because we've got the graph of x plus 4 already drawn for us. And if we look at the relationship between the red graph and the blue graph, we're going to notice things like, well, does it make sense that these 2 points are on both the red graph and the blue graph? And why? Because the square root of 1 is 1. So it makes sense that that point stays the same. And the square root of 0 is 0. So those will be two very important points when we learn how to graph all square root graphs. That when the y value is 0 or the y value of 1 of the original function inside, the square root of 1 or the square root of 0 makes no difference. It doesn't change anything. You can also look at other nice points on your original graph. For example, I'm going to call this a nice point, 0, 4. And I'm going to call 1, 5 a not nice point. So now we have to think, now why would I call 0, 4 a nice point and 1, 5 a not nice point when I'm trying to find the points on the square root graph? You can square root 4 pretty nicely. Square root of 4 will be 2, so I know that on my blue graph I'll have 0, 2. 1, 5, well, it doesn't square root nicely, but I would know on my blue graph I'd have 1, square root of 5, which isn't as nice to graph because it doesn't happen to be right on one of our grid points. Something else interesting happens when we compare our blue graph to our red graph. Now, I'm going to be talking about y values, and I'm going to be talking about y values being above my original graph. And when I talk about my original graph, I'm going to be talking about the red one. And I'm going to be talking about y values being below my original graph. Would you agree that the point 0, 2 on the blue graph is below the point 0, 4 on the red graph? Does the language make sense? Because we're talking about the y values and it's underneath the original graph. So we notice that sometimes our blue graph is below our red graph. Would you agree everywhere where I've highlighted it so far, our blue graph is below our red graph? In fact, that's what we're most used to. If I have 9 and the square root of 9, which one's smaller? The square root of 9 is 3. But there are some cases where you can square root a number and it's actually bigger than what you started with. For example, what is the square root of 1/4? One half. And 1/2 is bigger than 1/4. So we notice that there are some values where when you square root, the number gets bigger. There are some values when you square root, the number gets smaller. Anytime you square root a value, a y value that's bigger than 1, it's below. And anytime you square root a y value that's in between 0 and 1, like 1/4 or 1/9, it's going to be larger than what you started with. Here's another example. Now, if you had to use transformations to graph this, what would you have to do first? You have to factor out that negative. So you would have to first write it as negative bracket x minus 2. And if you did your transformations, you would first multiply your x values by a -1. That would be a flip over the y-axis, and then move it 2 to the right. Can you see that that blue graph is a flip over the y-axis and move 2 to the right? So again, we could use transformations to graph this. However, in this case, you might like this new technique even better. The new technique says graph the inside function, negative x plus 2. If I graph negative x plus 2, that's this red graph right here. Label the points where the y value is 1 and where the y value is 0. In other words, what's our x-intercept? Would you agree that that's at 2, 0? Right? And since we have a slope of -1, we could go up 1 over 1. We would have the point 1, 1. And those points are going to be the same on your square root graph as they are on your original graph. You could find another nice point. You could go on your graph and say, oh, right here I have -2, 4. So that means on my blue graph, I'm going to have -2, 2, because the square root of 4 is 2. And finally, you're going to indicate that when your y values on your original graph are bigger than 1, then your y values on your square root graph are going to be below. Does that make sense? That all of those parts there are always going to be below the red graph. And where your y values on your original red graph are between 0 and 1, the y values on your blue graph are going to be slightly above. We still have the same shape of our square root graph that we had before. But once we start to square root other things, we're going to have interesting shapes appear. So if we sort of highlight on the next page, we can highlight all of these things that we've seen. Okay, here are the characteristics. Where the y values are 0 and 1, those points stay the same. Okay? Invariant points, then points with these y coordinates lie on both graphs. That means that they're going to stay exactly the same. Where the graph lies between y equals 1 and the x-axis. So there's a very short way of highlighting what that. If your graph, your y values are between 0 and 1, your new graph will be above your original graph. And where the y values are above y equals 1, your new graph, your square root graph, will be below. Finally, one of the things that I didn't talk so much on these last graphs, but we should, is I'm going to quickly go back to these last ones and say wherever my red graph was negative, I didn't draw my blue graph. Why? Well, you can't take the square root of a negative. So if your y values are negative, here, when everything is less than -4, my y values are negative, there is no square root graph that exists because you can't take the square root of a negative. On this one, whenever my x values are bigger than 2, my y values will be negative and no square root graph exists. So we already know we can't take the square root of a negative number. And we'll use these characteristics because with these characteristics, these little ideas, we can graph any square root graph now. Sometimes in a question like example 1, they'll give you the graphs, and they won't give you the equations. So if you're given the graphs and not given the equations, you're basically going to follow the properties. First thing you're going to look for where are the points where y equals 0 and y equals 1? Because those will be our invariant points. So on the first graph, here's where y equals 0. And it isn't even a nice point, but I can still label it. There's where y is equal to 1. Now this one's if possible. Sometimes this doesn't happen that you have any other nice points. But plot any other nice points if possible. Like I know I can take the square root of 4. I know I can take the square root of 9. So does another nice point appear on this one? Sure enough, I have 0, 4. So I'm going to have 0, 2. We have up here somewhere where it's 9. It looks like it's at 2.5, 9. So I would have 2.5, 3. Those would be nice points. Step 3. Between 0 and 1, and again, that's your y values. Between 0 and 1, the graph is above. Maybe I'll say the new graph is above. Above y equals 1, when your y values are bigger than 1, the graph is below. So on our graph, between 0 and 1, we have to carefully draw it above. Not careful enough. Try again. So you need to be able to see that it's above, and then after, below. So this is where you want your pencil sharpened nicely so you can show that it is above. We need to be careful. We can't over-exaggerate it. Okay? That would be considered an over-exaggeration, and that over-exaggeration, it's not much. I tried to under-exaggerate an over-exaggeration. Whew. But what have I done with the purple? I've gone a little bit back in time. You notice that now the purple doesn't pass the vertical line test. It's no longer a function because I went back too far. I mean, really bad examples in purple would be like, yeah, wow, that's really bad. I mean, I show that it's above, but I'm going way back in time. You can't go back in time. So we need to show that it's above, but it's above and still between 0 and 1 and still has to pass the vertical line test. Sometimes your above line, they will give it to you if it's like right on top of it because that's about all you could do. It's so tight that it's hard to show. This would be our final graph. So what have we done? We found our invariant points. We plotted other nice points if possible. And then we showed that we knew that when the y values were between 0 and 1, our new graph would be above. And when the y values were above y equals 1, then our new graph is below. So this question also said, can you state the domain and range of your new graph? So the domain of my new graph, the blue graph, is now x is bigger than or equal to -2, and my range, y is bigger than or equal to 0. So I'll do the first one in interval notation. I'll do the second one in set notation. I'll do the second one in interval notation so we can see both notations, and you can choose which one you'd like to use. Example B. Second one, again, are there any points where it's 0 and 1? Yes. We've got 0 there, 1 is right there. Are there any other nice points? Not really. Okay. You know the square root of 3 is? Around 1.7. So if you know the square root of 3 is around 1.7, you could do that. Right? We know the square root of 3 is not bigger than 2. But there are not really any nicer points on this one. Now, between 0 and 1, when the y values are between 0 and 1 on our red graph, our blue graph has to be slightly above. And when our y values on our red graph are above y equals 1, our blue graph will be below. There's our final graph. The domain for this one, in interval notation, there is no smallest value, and it goes from -infinity up to 6 and includes 6. And our range, it does have a smallest value of 0 and goes to infinity. Always used round brackets with infinities, and square brackets indicate that that value is included. Question number 5 for practice.